Hey, welcome back. So 6.6, we're talking about vectors. Vectors are used extensively in physics. And what is it? It's a quantity that has both a length and a direction. So it represents two numbers at the same time. And you could use, whatever you want, really. You could talk about wind for one thing. So wind has a direction and then the speed of the wind on top of it. Okay, so anyways, defining a vector from the book, it's a quantity that has both a length and a direction. Okay. So again, an example of something that's a vector, wind. Wind blowing 35 miles per hour at north 5 degrees west. Okay. The first thing we're going to note is kind of a geometric way of talking about vectors. Okay, so this is a 5, not an S, if you're wondering. And I could represent wind blowing 35 miles per hour using an arrow. Okay, so north 5 degrees west would be about right here. And then we want an arrow that has length 35. So the length of this arrow would be 35. And it's directed at north. So this is north, west, east, and south. If you remember the bearings section from previously in the book. Okay, so it's that arrow thing right there. That's the vector. Okay, so we're going to develop sort of the geometry of the vectors, and then we're going to develop kind of just working with them algebraically, okay, without all the little pictures. Okay. But it's used in physics for force and just pretty much anything in physics. They use vectors. Okay. So anyways, we'll use these arrows, and the book's going to call them directed line segments. Okay, so directed line segments represent vectors. Okay, and we can basically just put them anywhere in the plane here. I don't have to put them at the origin. Eventually I'm going to put them at the origin though, and sort of put them in the XY plane. But anyways, here's an example of a vector, and it has two parts on it. So it has the initial point and then the end point. So P is the initial point where it starts. And then the end point, which they often call the terminal point, that's Q. That's where the arrowhead is. Okay. When we talk about it in general, the book will write it with kind of bold-faced letters, but what we do to, instead of the bold-faced letters, we're going to put a little arrow over top of it, like that. So it's not a double-headed arrow, it's just the top has an arrow on it. Okay. Then we could talk about the magnitude of this vector, and that's just the length. So they're going to call that magnitude or length. Okay. To show that two vectors are the same, and this comes up later on if you kept taking math and physics, it's always an issue. How do I know that two vectors are the same? You can do it geometrically. You just have to verify they have the same sort of direction. And to say it has the same direction, you could also think in terms of slope. Okay, so there may be more than one way to kind of do this. Anyways, let's look at that. Equality of vectors. And then we'll look at an example from the book where they ask you to show that two vectors are the same. Doing this in sort of our current setting, the geometric, which just, I think of geometry just means pictures, right? So geometrically, to say that two vectors are equal, how can I do that? So how do I verify these two vectors are equal? First, you need to show that they have the same magnitude. Okay, so that verify they have equal lengths. And in order to do that, you could just use the distance formula. It's just like the modulus when you're dealing with complex numbers. So it's the square root of the x and then the y sort of parts squared. I'm going to give you an example so it'll be more clear. But it'll come down to the distance formula. And then you have to make sure that also they have the same direction. And if you're not given the sort of an angle of direction, you can use slope. Okay, so good old slope from basic algebra. Okay, so let's take a look at an example here. This is problem 2 in the book. And they give us 2 vectors, and they put them in the plane, which is awful nice of them. So first vector u is starting at 0, 0, the origin, and then it goes to -4, 6. 2, 3, 4, 5, 6. And then so this, I'll call it vector u. And again, when they write vectors in the book, they'll use a boldface u, but for us, we just put an arrow over top of it for vector. Okay. And sometimes that gets annoying. So if you're like in a linear algebra class, they probably won't even draw the vector arrow. They'll just assume that you know they're talking about a vector. So sometimes you have to be able to read in between the lines. Just like in our normal conversations, we don't, you know, sometimes we'll use slang and stuff like that. Especially if you're like an older professor who's tired of explaining things, they may use a lot more slang than like I would as a community college professor. Okay. Anyways, this other guy starts at 2, -1. And let me label this other point on the vector u. So this is at -4, 6. So the other vector v starts at 2, -1, and then goes to -2, 5. 1, 2, 3, 4, 5, right here. So they look like they're about the same, right? But that's not enough. You can't say, well, I think they look the same. Let's base the airplane design on this. You know, no, that's not going to work. So first, I'm going to verify that they have the same length, and I'll just use the distance formula. The magnitude of vector, and this is vector v over here, by the way. The magnitude of vector u is the difference between the x components squared. So if you look at the x components, where are those? -4 and 0. So you just take the difference, -4 minus 0, and square it. And then plus the y coordinates. So that'd be 6 and 0. So plus 6 minus 0 squared. Sorry about the weird colors. Kind of got mixed there. Anyways, this will be the square root of -4 squared is 16, plus 6 squared is 36, and that'll equal the square root of 52. I don't need to simplify it. I'm just looking to see if v has the same length. So if I get square root of 52 again, I'll be good. So here, this guy, again, you just take the initial point and the terminal point, and this other point is -2, 5, by the way. Okay, so -2 minus 2, the x coordinates, and square that, and then plus 5 minus -1, and then square that. And we good. So -2 minus 2 is -4, -4 squared is 16, plus 5 minus -1 is 6, 6 squared is 36, and sure enough, they have the same length. Okay, so that part, you know, equal length, we verified that. Good. Go on to the second part. Okay, so the second part then is slope. Just look at the slope and see if they're going in the same direction. So the slope from vector u is going to be rise over run, right? y2 minus y1 over x2 minus x1. So you go 6 minus 0 all over -4 minus 0. So I get -6/4, which is -3/2. And then the slope of vector v, again, y coordinate minus the other y coordinate, 5 minus -1, all over -2 minus 2. Okay, so 5 plus 1 is 6, all over -2 minus 2 is -4. And sure enough, Same length, same direction. In other words, these two vectors are equal. So hence, we may conclude vector v is equal to vector u. Okay? Okay, great. We want to talk about sort of the geometry of what happens when you add these things. So you know, if you add two numbers, there's not too much involved. We kind of have that sort of memorized. And you can think of it geometrically as well if you add two numbers. So if you add 3 plus 2, you know, here's 0, 1, 2, 3, 4. If you add 3 plus 2, you go 0 to 3. And then plus 2 will move you 1, 2 more. And so you end up at 5. So there's not too much going on, really, when you add numbers. But when you add vectors, it's different, okay? And we want to see how that looks. You can also subtract vectors. You're not going to be able to accomplish all the cool stuff like we do with the real numbers, okay? Like if you wanted to multiply vectors, it's not going to work kind of like you would think, okay? In actuality, there'll be two types of multiplication. One is the dot product. So they call them products, like the product of two numbers is like multiplying them. They have the dot product and they have the cross product, okay? And each one has its own kind of geometry associated with it, okay? So we will focus here first on adding and subtracting, and then we'll focus in on multiplying, not two vectors together, but a number times a vector. Okay, so it gets kind of really weird in that way. And you could look at in math, if you kept taking math, you would look at sort of like abstract versions of these ideas. Like you would have maybe some numbers and then some other kind of objects, and instead multiplication would mean rotating things in space, and it could get really, really cool if you keep on at it. But there are not too many jobs in there. It's really competitive if you want a job in that field. So you could always become a teacher, but you know, people don't like being teachers. The teachers get a lot of, can be kind of a bummer. But anyway, first, let's, instead of starting with addition and subtraction, let's start with scalar multiplication. So it's not multiplying, long story short, and I'm sorry I'm babbling, it's not two vectors being multiplied by each other. You're literally taking a regular number that we love and adore and multiplying it onto a vector, okay? And so what does that look like geometrically? So here, let's take this vector, it's going straight up, call it u, vector u. If you multiply it by 2, it'll kind of stretch it out, okay? It's kind of like an amplitude type idea. So 2 times the vector u would be this thing. You can multiply, if you multiply by something smaller, it'll shrink it. So if you multiply like 1/2 times u, it'll shrink it. If you multiply by a negative, it'll send it in the other direction. So negative u, geometrically, that will just turn it upside down like this, okay? So that's kind of the idea that we're dealing with geometrically. And then scalar multiplication turns out to be real easy algebraically. So the counterpart in algebra will be a lot easier, I think, on us. Let's look at the addition subtraction idea. Okay, so section 5, vector addition and a vector subtraction. So this is where you take two vectors and you're combining them. Okay. Okay, so first, again, this is sort of the geometric picture, and later here we'll look at the algebra type, the non-geometric version. So what we're going to end up with is what's called a resultant vector. And you'll see this in physics. Basically, if you have a bunch of forces acting on an object, all you have to do is add up those forces, and that will be the result of the force acting on the object. So if you have like some big guy pushing you to the right and some little guy pushing you to the left, ultimately you'll go to the right, but not as much as you would because there's a little guy pushing you in the other direction. But to figure out the overall force, all you would have to do is kind of add in those two forces. Okay, and that's the idea. So you have, let's take a look at the picture. I have maybe one vector going like this, call that vector v, and I have another vector going over here, call that vector u. Okay. To add the vectors together, what you're going to do is just kind of borrow the vector. So I'm going to borrow vector v, and I'm going to sort of tape it to the end of vector u. Okay, like right here. You see how that's just vector v, but kind of moved in the plane. Okay. Okay. So what is the result of adding these two together? It's the vector that goes from the initial point of u to the terminal point of v. Okay, so that blue vector I just drew right there, that's u plus v geometrically. Okay. Okay, so one thing, the one way to look at that is kind of like the diagonal of a parallelogram. So one way they introduce it in some of the books is to just draw a parallelogram based off of these vectors. So let's take two more vectors, maybe one going over here, and maybe one like this. So this is vector, and they just coincidentally happen to be at 90-degree angle of each other. But what you do is kind of form a rectangle, or yeah, in this case it'll be kind of a rectangle. In general, it'll be a parallelogram. So I sort of translate this vector v over to the terminal end of u, and then you could translate the vector u over to the terminal end of v, and you form a parallelogram, and then the diagonal of that parallelogram is the resultant vector, u plus v. So this time I'm drawing it in yellow. Okay. All right, what about subtraction then? Well, it kind of works in the same way, because you can always think of subtraction as the addition of a negative integer. Okay, so what did he just say? Think about it. U minus v, so vector u minus vector v is the same as going vector u plus the negative of vector v. Okay, so let's watch how this works. Okay, so I can, again, I'll just work with these two vectors to the left. This is vector v, and this is vector u. So what I'm going to do is kind of take vector v and attach it to the terminal end of u, just like I would for addition. But then, instead of drawing it in this direction, you take the negative of it. So you draw it in this direction. Okay. And then the difference of u and v, because this is negative v, it's just the same as the sum would be. So you go from the initial point of vector u to the terminal point of vector negative v. Okay, so this would be u minus v. Okay. A quick way to do it is just to connect the tops of these two vectors together, because you just kind of see if you translated u minus v up, it would just attach right here. So this would be u minus v. Okay. So again, let's take a look at the other scenario that I created. Here's vector v, and here's some other vector u. So to get the difference between the two, you can kind of do the long way. You can just sort of attach negative v to the end of u. And then the difference is just going from the initial point of u to the terminal end of negative v. But the truth is, you can always just kind of connect the terminal ends together, and that gives you u minus v. You have to be a little careful about the directions. V minus u and u minus v are different, right? They're going in different directions. So usually when I do it, when I first started, I would always just kind of think in terms of adding in the negative vector and then connecting in the same way that I would do for addition. Okay? Okay. The next thing we want to do is rewrite all of our vectors in terms of this unit vector notation. Okay? So it kind of gives us a way of formalizing vectors a little bit more. So we have unit vector notation. Okay. So first off, we introduce this thing called the basis vectors. Okay. And, you know, literally, you can pick anything as your basis vectors as long as the vectors aren't kind of going in the same direction. You can use anything. But when they're perpendicular like this, it's really nice. It makes everything a lot easier. So we use these two vectors here for our basis vectors. And any vector in the plane you can represent using multiples of these multiples of sums of these two vectors here, these two unit vectors. And they're unit vectors because the lengths are 1. Okay, so they'll say unit is kind of like 1. Okay, like the imaginary unit is kind of like 1. All right, so anyways, you know, when we write these things out, we're going to put a little hat on them. So in the book, you'll see it's a bold-faced J for this guy going up. But when we write it on our paper, we're going to put a little hat on it. Okay, so you see that little corner hat thing? That's vector J. And then this vector going to the right is vector I. Okay, and this point here will be 1, 0. This point here is 0, 1. And the length of these vectors, so the length of the I vector is going to be the square root of 1 squared plus 0 squared, which is the square root of 1 squared, which of course is 1. And that will be the same as the unit vector j, because you know it was just done be 0 plus 1 squared, which is the square root of 1 squared, which is 1. Okay, great. Excuse me. So for any point in the plane, you could represent them in terms of these vectors. So for instance, let's say the vector 3, 4. So 1, 2, 3, and then 1, 2, 3, 4. Okay. So let's call this vector u equals, well, we only know it geometrically. We want to kind of find a different way to represent it. So as a sum of two vectors, the bottom vector is a scalar multiple of the I vector. So the distance from here to here is, well, what is that? That's 3i. Okay. And then this vector from here to here is a multiple of the j vector. So that's 1, 2, 3, 4j. All right. So if you took those vectors, you know, and you translate them and use the addition rule, the geometric rule here, you would have 3i plus 4j equals this vector u, just from what we know about the addition of vectors. So you can write the vector u in that way. You can write it as 3i plus 4j. Kind of cool. Okay. And then we're going to be able to do all kinds of operations with this, and it's going to make life one heck of a lot easier. So typically we're not going to worry about having to do these geometric kind of additions. It'll just turn into adding components together. So if you want to add two vectors, you just add the I components together and add the j components together. Okay. Anyways, to get the length of this vector, it's just like what you did with complex numbers, and it's a lot like a complex number, right? It's just instead of having the a plus bi, you have 3i plus ai plus bj, right? So in this case, it would be 3 squared plus 4 squared, which would be the square root of 9 plus 16, which would be the square root of 25, so its length is 5. And then later we can also talk about kind of a polar version where we can consider this angle in here, and we'll get there. Okay. Okay. Right. So let's look at one of maybe the questions, checkpoint in the book. If I can get my pen to work, that would be great. Checkpoint 2 in the book. They want you to sketch the vector v, which is equal to 3i minus 3j. And it's almost literally just plot the point 3, negative 3, and draw an arrow to it. I mean, that's what it comes down to, all right? Don't overthink it. So sketch that and find its magnitude. And eventually we'll want to do things like find the direction in a way that doesn't include the slope. So anyways, let's graph it in the xy plane. So I go 1, 2, 3, and then down 1, 2, 3. There it is. So just like I said, plot 3, -3, and then draw an arrow from the origin to it. And that'll be our vector v. Its magnitude then, so the magnitude of v is going to be the square root of the component squared, right? So in this case, 9 plus 9. So it'll be 9 plus 9 is 18. That'll be, what is that, 3 root 2? 3 root 2. So 18 is 9 times 2. And then you could split up that square root 9 times square root 2 is 3 root 2. Okay. Okay. One thing we want to be able to do is, given 2 points, create a vector to represent the line in between those 2 points. So representing, a lot of this is kind of, you'll apply it in your physics class and later on, and if you kept taking math, you would take it in Calc 3. You would see a lot of work with vectors. Anyways, representing arbitrary vectors. So a lot of this seems kind of unmotivated and kind of like, why am I doing this? You just have to have a little bit of faith that this will pay off. Anyways, 14, we want the vector going from P1, which is 2, -5 in the plane, to the point P2, which is going to be 6, 2. Okay, drawing the picture probably isn't going to be too much of a help. So anyways, you can go 1, 2. Pen is being jerk 1, 2, 2, 3, 4, 5. So I have this point, and I want to go to 1, 2, 3, 4, 5, 6, 2 up here. Okay, so I want the vector representation for that vector there. Okay. Right. So how does this work? The vector P1, P2 is going to equal, well, you just take the difference of the x coordinates for the first component, quote unquote component. So 6 minus 2i. That will be this distance here, okay, which is 4. And then plus the difference between these two components. So it would be 2 minus -5. And let me see my office hours. We're still going on. So 2, where am I? 2 minus -5. 2 minus -5, which is basically just this distance right here. Okay. And that will be our j component. So that will be 4i plus, it looks like 7j. And we could reposition that vector at the origin if we wish. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay. And there it is, repositioned at the origin if you want. Okay. Okay. In general, then, and you have to be a little bit careful about the order. So if I want the arrow from P2 to P1, I would have to go in my P2, P1 is different, right? This is the opposite direction, and it would be 2 minus 6i plus -5 minus 2j, right? So that would equal -4i plus -7j. And there's no reason to put you just write minus, but anyways, of course that will just go in the other direction. So you have to be a little bit careful. In general, given 2 points, P1, which we'll say is x1, y1, and some other point P2, which we could say is x2, y2, the vector P1, P2, going from P1 to P2, will be x2 minus x1 I plus y2 minus y1j. Okay. Okay. So now that we have these other representations for the vectors, we want to just work with those representations. We don't want to have to work with the pictures, because honestly, you can put vectors in 3 dimensions, and trying to draw all this baloney it becomes impossible unless you're Rembrandt, okay, or Picasso or whoever. How do we perform the geometric, the addition, the scalar multiplication? How do we perform those without the pictures? So I'll call it non-geometric operations, non-picture operations. it turns out to be real easy. Okay, first, adding and subtracting. Literally, all you have to do is add up the I components together and add up the j components. So let's say we have u is 2i minus 5j, and then we have v is negative 3i plus 7j, and then we have w is negative I minus 6j. Okay. All right, so let's look at some of the problems. 21, they want to know the sum of u plus v. Right, so how do I do that? Well, you just add up the I parts. So 2 plus negative 3i, and then plus, then you add the j components together. So that'd be negative 5 plus 7. It's really that easy. So you end up with negative 1i minus plus 2j. And if you drew it out, you would get basically you would see that parallelogram like you would. It works, believe it or not. You try it. Try it on your scratch paper. Pause the video and try it. Let's look at v minus u. Okay? So v, the first component, negative 3, and then minus the u component is minus 2. That'll be I. And then plus the j component of v7 minus the j component of u, which is negative 5j. And it's really just that easy. It's just too good to be true. Negative 5i plus 12j. Did I go minus? Yeah, I minus them, right? So it was negative 3. So I got something funny in my notes. Maybe I wrote it down wrong in my notes. I gotta check my notes real quick. Hold on. No, I'm right. I don't know why my notes are messed up. Whoops. Okay. Anyways, let's look at the scalar multiple types then. Part B, doing this. So geometrically, this is the one where you're stretching a vector, and it's not really a vector times a vector, right? We'll have interpretations of the product of vectors coming up soon in the next section. Okay, so anyways, a scalar multiple, like k times v, all you have to do is multiply the two components. Okay, so if v was equal to ai plus bj, and basically, I'm calling this thing as a component of the vector. A is a component, b is a component, okay? So k times v is just going to be ka, believe it or not, plus kb, j. It's really that easy. And if you think about it, it works geometrically, right? Because if you had this vector, say u, and it equaled 0i plus 1j, so it is the j vector. If you multiply it by 2u, you just get 0 times 2 is 0i, plus 2 times 1 is 2j. So you just get something that is twice as long. Okay. Anyways, let's look at some more of these then. 27, 5 times vector v. I've lost my vector v, is way back here. Negative 3 and 7. So v is negative 3i plus 7j. Sometimes in later books, like when I teach it in calculus, I actually use a different notation. It looks like this, negative 3, 7. So it's like an ordered pair almost, but it's not really an ordered pair because you can't do operations on ordered pairs like we're doing here. But sometimes a little easier to work with it like that. So if you see that in the future, they're just talking about vectors, usually. Sometimes they're define it in weird ways, but usually it's just a vector. So anyways, 5 times v will be, multiply each component by 5. So negative 15i plus 35j. Let's look at number 30. We want negative 7 times w. So I need my w vector, negative 1, negative 6. Right? So you just multiply each component by -7. So I end up with 7i plus 42j. Okay, pretty easy, huh? How about something like w minus w? So there's just an example, w minus w. Does that equal 0? Well, no, not quite. It equals the 0 vector, which is different, believe it or not. So what is w minus w? So w, we said -1 minus 6. So if I subtract it would be -1 minus -1, j, or sorry, I, and then plus -6 minus -6, j, right? So this will be 0i plus 0j, and that's called the 0 vector, okay? So it's not 0. It's a little bit different. I mean, they sort of look the same if you were to graph. Well, I guess you couldn't even graph the number 0 in the plane, right? You need an ordered pair. So this is like more like an ordered pair than just a regular number. So this is the 0 vector. So the thing is, you can't do things like add 0 plus a vector. You can't add, this is not a vector. 0 is not a vector, so you can't add 0 to, you can multiply 0 times vector w. That would give you the 0 vector, okay? But you can't do this. This is not allowed. So you could add the 0 vector plus the w vector. That'll give you the w vector. But you can't, add a scalar to a vector. So there's some weirdness going on there I just want you to be aware of. So there's a bunch of sort of other properties on page, let me find it, page 777. There's a ton of other properties, other weird properties of this vector universe. So I just want you to note those and talk about one of them. So note important properties on page 777. So one of the properties is this fact, that if you have a constant or a scalar, so they call the, when you have, what's the difference between a regular number like we're used to dealing with in a vector? The regular number is called a scalar, okay? And the scalar just has one kind of dimension to it. Like, it's not like a vector. A vector has two things to it, right? Like wind, direction, and speed. The scalars only have one dimension to them. They only represent one thing, okay? So this value c is a scalar. I'm sorry if I did not make that clear. So a scalar is just like a regular number that we deal with. A vector is, so a scalar is just a real number. Like the number 5. And I don't mean like it has to be an integer. It could be a fraction. It could be, the number pi. But it's just a number that doesn't have a direction or anything else associated with it. So anyways, if you have a scalar times a vector like this, the magnitude of that thing, you can kind of factor out the scalar. Okay, kind of. So anyways, let's take a look at and prove this factoid. So suppose you have a randomly generated vector v. Let's arbitrarily call it ai plus bj. Thus, we can note that c times v will just be cai plus cbj, and then we can find the magnitude of that. Okay, from the definition of magnitude, the magnitude of CV then is going to equal the square root of CA squared plus CB squared. Okay. Then we could rewrite that as c squared a squared plus c squared b squared. And then we could rewrite that as a square root. You can factor out the c squared, right? So then you have a squared plus b squared. And then the square root of a product is the product of the square roots. That's one of our fundamental factoids. And then the square root of something squared, you would think that's just c, but it's not. Okay, so if you have like -1 squared and take the square root of that, that's not equal to -1. It's equal to +1. Okay, so you can't really say it's equal to c. You have to say it's the absolute value of c times the square root of a squared plus b squared. And of course, the square root of a squared plus b squared is just the magnitude of this vector v. So we end up with the absolute value of c times the magnitude of this vector v, which for weird reasons turns out to be kind of important. The next thing we want to look at is kind of reformalizing all these vectors to just be standardized. For instance, if you're looking at kind of what they call a vector field that's describing maybe wind, you may have a bunch of arrows, kind of like I'm looking down onto a bunch of wind blowing around, and maybe the wind is going like this. It turns out to be kind of easier to kind of figure out what's going on if all the vectors are the same length. You get a better picture of the wind for weird reasons, because maybe you'll have wind going really, really fast in this direction, but then the other vectors around it are kind of still small, and it's kind of hard to tell what's going on. So sometimes you want to do what is called creating the unit vector, which takes any vector and turns it into a vector with length 1. Okay, so this is section 8. Okay, the unit vector. And so basically the formula that we use here is, so given some vector v, the unit vector u will equal the vector v divided by the magnitude of vector v, which is basically just multiplying by a scalar. Okay? And what does this do? The formula resizes the vector so its magnitude is 1. Okay. You know, weirdly enough, there's certain things we'll want to do with vectors. Like we want to add them all up sometimes, and to get kind of an idea. So if you drew like a circle, you'd want to go around and sort of add up the vectors to get an idea of how much is going out from this source. Okay, so you end up having to add up vectors, and in order to do that, you're going to have to turn them into unit vectors. And this is all physics stuff. It's all, you know, dealing how people predict wind patterns and stuff like that. They use vectors. You've probably seen little vectors when you watch the Weatherman. Anyways, so you resize the vector so its magnitude is 1. Okay, so let's look at this in action. So we have vector v here is 3i minus 4j. And I want to rewrite it so it has length 1. So you find the magnitude of v. That'll be the square root of 3 squared, which is 9, plus 4 squared is 16. It'll be the square root of 25, which is 5. So you take vector v and basically divide it by 5. If you'd rather think of it as multiplying by 1/5, that's the same. Okay, so you end up with just multiply the components by 1/5. 3/5 I minus 4/5 j. All right, and then you could see this thing has, if we call it, let's call it something else, let's call it u and find its magnitude. Its magnitude will be 1, magically enough. Okay? So you'll have 3/5 squared plus negative 4/5 squared. That'll equal the square root of 9/25 plus 16/25, which is square root of 25/25, which of course is the square root of 1, which is, yeah, it works. Okay. One last thing is rewriting vectors in kind of like the polar form, like we did with the complex numbers, except we're not going to call it polar form. We're just going to say we're giving vectors in terms of magnitude and direction. My Roman numerals are going all the way up to 9 today. Vector in terms of magnitude and direction. Okay. So if you remember the polar, maybe we can just cut to the chase here. The polar form for a complex number in the rectangular system, how did that work? It would be r times cosine of theta plus I sine theta, okay? Where r was the modulus, but it's really just the magnitude in this setting. So in our setting now, we have AI plus bj. Instead of r, we'll have the magnitude of this vector. So let's give this vector a name. Let's call it v. That's my cursive v. So it'll be the magnitude of v instead of r times cosine of theta I plus sine of theta j. So you can kind of see how it's exactly the same thing, right? Let's make that a little bit more clear by kind of going through the process again and how it worked. So you'll have a vector in the plane. This is our vector v. Oops, I should put a little arrowhead on that. And we could describe it, now with these components in terms of the unit standard vector ai plus bj. So this distance on the x-axis is a, this distance on the y-axis is b, and then we could describe it in terms of this angle and the distance of vector v, which is given by the magnitude. Okay, so I recall that the cosine of theta will be adjacent all over hypotenuse. So the a in our vector will be the magnitude of v cosine theta. And then I recall that the sine of theta is equal to opposite over hypotenuse. Solving for b, I get the b component is equal to the magnitude of v times sine of theta. Okay, so ultimately then I can kind of rewrite v, the vector, in terms of magnitude and direction, the magnitude of the vector and the direction theta. Okay, so I'll have the first component is v cosine of theta I, and then plus magnitude of v sine of theta j. And of course, all the other kind of formulas work out. You see the Pythagorean theorem just gives you a formula for the magnitude of v. You can figure out, if you need to figure out direction and you're given this form, you can find it by taking the inverse tan. If you're given this unit vector notation, ai plus bj, the direction, instead of using slope, you could say theta is equal to tan inverse of opposite over adjacent. Okay, so let's see if we can apply this to one or two. So number 65 in the book, it's on page, just two more questions and we'll be done. 65 in the book's on page 782. And it's on some guy throwing a football. So a quarterback releases a football with a speed of 44 feet per second at an angle of 30 degrees. So you can imagine that the guy is maybe here and an angle of 30 degrees. And the vector has a length of 44 feet. 44 feet per second is the length of that thing. Okay, so when they say speed, they mean the magnitude. Okay. All right, so over here to the side, I just note the. So what does the question want? Express the vector in terms of I and j. Okay, so they're giving us basically this form, and we want to turn it into the other form, or just write it this way if we can't simplify it. But I think we're going to be able to simplify it. So this one, the speed was given as 44, so that'll be the magnitude of the velocity. So velocity is speed and direction. Okay, when they talk about speed, they just mean the actual value. Like I'm going at 44 miles per hour. Hey, what direction are you going? If you need to know the direction on top of the speed, then it becomes a vector. Okay, but when you just talk about speed, you're not talking about direction, so you're just talking about magnitude. Okay. Also then theta is given as 30 degrees, so we can write our vector up. Our vector v will be 44 cosine of 30 degrees. We want the ij notation, plus 44 sine of 30 degrees j, and they want you to simplify that. Okay. So used to converting things, I thought I had to convert this to some other form, but it's really just a matter of simplifying. So I apologize for what I said. 44 cosine of 30 then is just 1/2. Oh, wait a second. Cosine of 30 is √3/2 for cosine. And then plus the sine of 30, which is sine of pi/6, is the 1/2 that I'm looking for. So this will be 22 √3i plus 22, just 22j. Okay. From this number, you can actually figure out the, you can't do very much with it. It's probably better to have it in the other format, right? Because you could see the angle, you could see the velocity. I don't know. Okay, let's look at this last example, and this will be your video quiz as well. So the resultant force is what we're talking about. And I mentioned this earlier in the video. The resultant force is what happens when you add up all the forces. So usually we talk about tugboats. So just thinking today about the big boat stuck in the Suez Canal, and so the tugboats are definitely, if the big boat is kind of like sitting right here, the tugboats are both want to push in a particular direction, right? So maybe one's pushing in this direction, and then maybe one's pushing in this direction like this. Or maybe we put the boat at the origin. Maybe that's a better way to think of it. And so then we have a boat pushing it out like this in one direction. And then because the boats aren't like lined up with each other, so that one boat is pushing like this, but the other boat isn't directly behind that boat, right? So it's kind of angled at a little weird direction, the tugboat, and it's pushing then maybe in this direction. And thank you. So one boat is kind of pushing in this direction, one boat is kind of pushing in this direction. The resultant force of that, so maybe this is force 1 and this is force 2. The overall force you can find by adding up those two vectors. Okay, so force 2 plus force 1 will basically tell you the force that's acting on that ship that's sitting in the Suez Canal. Okay, and it's just I think it's one of the fundamental laws of physics, basically. It's one of the 3 fundamental laws. It's probably the 3rd one. Let's look at this point. So this is the video quiz. Checkpoint 9. Video quiz, video quiz, video quiz. In this case, what we're talking about, and I guess no, let's just keep with what the book says. Let's not get creative. Let me find the problem. There's 2 forces, and you can pretend they're tugboats or something. Force 1 and force 2. They tell you the magnitudes of these forces. One is going in the direction of north 10 degrees east. So if we think about our kind of northeast, southwest, north 10 degrees east is 10 degrees away from north. Okay. So what did they say? The magnitude of force 1 is equal to, and this will not be a tugboat because it's only 30 pounds of force. I think a tugboat could do more than that. 30 pounds of force, and its direction is north 10 degrees east. Force 2, okay, so that's force 1. Force 2 is given 60 pounds of force, and its direction is north 60 degrees east. Okay, so if I draw that guy, 60 degrees will be a lot farther down, so 60 degrees east, and it'll be longer as well because it has more force, so the vector will look longer. So maybe draw it out there or something. We want to know the resultant force, and then on top of that, we'll want to know the direction of the resulting force and the magnitude of the resulting force. Okay, so you could kind of assume, because they're almost going in the, and you can think of these as boats again, you know. So here is the green boat, whatever it's called, and then there's a tugboat pushing like right here, and then the other force is caused by maybe another tugboat pushing right here. Okay. You want to know the direction of that green boat, that cargo ship. What direction is that going to go? And you want to know the magnitude on that boat. Okay, so it's pretty easy to figure out. We're going to write these things in their form with magnitude and direction. So first F1, and we should have little arrowheads on them, but it's not that important. F1 is equal to 30 cosine of, and I have to use not the 10 degrees, but the 80 degrees, right? So it's 90 minus 10 is going to give me 80 degrees, plus 30 sine of 80. And then F2 is going to be 60 cosine, not of 60, but of 30, the 90 minus 60. 30 plus 60 sine of 30. And then to get the resultant force, all you have to do is add those two forces together by components. And I forgot my little i's and j's. If you want me to, I'm just going to squeeze those in. Okay. So the resultant force, I'll just call big F, is, if I go to my calculator, 30 cosine 80 plus 60 cosine 30 is approximately to 2 decimals, 57.17. And then 30 sine 80 plus 60 sine 30 is approximately 59.54. So again, I want two things now. I want the direction of the resultant force. So to get the direction, you go back to your tan of theta, which is going to be your y component. So the b value, which is here, and then the a value over the a value. So the b value, 59.54, all over 57.17. So theta will be tan inverse of that. And if you put that into your calculator, make sure you're in degrees, you will get 46.2 degrees. Okay. So the direction of the resultant vector is more closely aligned to that red vector. And that makes more sense because that one's exerting more force. Okay, so this would be kind of, I don't know how long it is. I don't know what the magnitude is yet. So let's get the magnitude as well. So the magnitude of F, you're just taking the square root of the component squared. So this will be the square root of 57.17 squared plus 59.54 squared. And again, going to your calculator, you'll end up getting 82.54 pounds. And you see that that's almost 90. But because they're not perpendicular, they're not acting in the same direction at the same point, it's not 90 pounds, right? It's still longer than both of them. It's just you have a combined force. So this is our F vector. Okay, so that was the video quiz. And it's really interesting stuff. If you like this kind of stuff, take physics. You'll love physics if you like this, to think about this stuff. And it all, you know, it all kind of, is a way of talking about the world around us in a way that in my opinion, is like perfect. When we talk about like human behavior and politics, it's not perfect to me. But with math and physics, there's kind of no argument, in my opinion. So it's a fun thing to visit if you're so sick of politics and all that stuff. Spend a couple of years just studying physics, and it's awesome. Okay, so and anyways, there's my plug. Thank you for watching as usual, and we will see you next time.